Hi, my name is Yibo Yang. I'm a PhD student at UC Irvine, advised by Professor Stefan Munt. In this video, I'd like to talk about my recent work on computationally efficient neural image compression with shallow decoders. Now, neural or deep learning-based methods for image compression have greatly exceeded traditional methods in terms of compression performance, but they also require orders of magnitude higher computation complexity. And this work aims to close this gap, and it's based on an observation that there is often an asymmetry between the computation budget we have for encoding versus decoding. So decoding complexity is often much more critical for things like streaming or mobile applications. So we'll take advantage of this and explore the performance of neural image compression at the lower limit of decoding complexity. So I'll start by reviewing classical transform coding, for example, JPEG. The way we encode an image is we divide it into little 8 by 8 blocks. And for each block, we'll take its inner product with a collection of filters, such as from DCT, discrete cosine transform. So each such filter is essentially a little pattern of signal, and together they span the space of all possible signals that can be defined on this little block. So we take all these inner products, and that results in a vector of transform coefficients. And then we'll quantize and convert them into binary with entropy coding. On the decoding side, we will take a vector of transform coefficients and use them to form a weighted combination of the filters. And we'll use the resulting sum as the reconstruction for that particular image patch. And we'll repeat this for all the other image patches. Now, neural image compression methods are essentially just a nonlinear version of the above, where we replace the linear transforms with deep neural networks, usually convolutional neural networks. And there's often a neural net component to the entropy coding as well. Now, recently there's an observation that these nonlinear transform coding methods essentially operate very similarly to their traditional linear counterparts. For one thing, the latent coefficients are very much localized. So if you take a coefficient vector corresponding to a particular spatial location, you run it through the convolutional decoder, you end up with essentially the reconstruction of a small image patch corresponding to that spatial location. And if you also decode essentially one hot vectors in the latent space or the coefficient space through this deep convolutional decoder, you actually end up with very much interpretable patterns that resemble the filters in classical transforms. And in this work, I even showed that the decoding transform essentially preserves preserves straight paths, in that it will map a interpolation in the latent space into essentially a pixel space interpolation in the image space. So what can we do with all of this? Well, I propose to replace the deep convolutional neural decoder with a much simpler and cheaper one, like the one from JPEG. And doing so will come at the cost of possibly worse ray distortion performance, but with greatly reduced computation complexity. But to maintain high compression performance, I propose to also make the encoder much more powerful, for example, using a transformer style architecture and iterative encoding. And this can be all justified theoretically using a novel decomposition of the loss function in neural lossy compression. Experimentally, this resulted in a new frontier in the performance trade-off between rate and distortion and decoding complexity. And we obtain rate distortion performance on par with VPG and the mean scale hyperprior at less than 50,000 flops per pixel. And improving the result on perceptual metrics is an interesting work um, for future research, as well as making the entropy coder more computationally efficient. Please check out our paper and code if for more details. Thanks very much.